It's time to start again. So what we've seen so far is we have a block cipher. And then we have some modes. Pick one mode. And then for the block cipher, we have seen so far des, and we have seen triple des. For modes, we have seen, well, ECB, which you really shouldn't use. You also shouldn't use single des. We have seen CBC, we have seen OFB, we have seen counter mode, and now on the exercise sheet you've also seen the cipher feedback mode. And that's pretty much the collection we normally see. There are some more combined things. Then other block ciphers, there's AES, and there are two versions of this, AES 128, AES 126, 256, sorry. So these here are the key sizes. Block ciphers typically have a similar design to what you've seen in DES. These don't have a Feistel design, so they don't have the left-right split. These have a funky design, which is like you split into 16 pieces, and then you arrange them in a square 4x4, and then you do some shifting in each row, and you do some shifting in each columns. And so some of them have the same rotation distance, some of them have a different rotation distance. So again, you're doing like lots of mixing, and then afterwards each of those cells goes through an S-box, and again the S-box is the main part for doing something nonlinear. So these are the current standards. There are also some other ones which are basically, well, closely related to DES. There's a cipher called Crescent. Which is taking the small hardware footprint of DES to, well, takes it even further and says, well, instead of having these different S-boxes, how about we all use the same S-box? So this is like DES, it does a Feistel construction and then uses only one single S-box. So this is DES-like. Same S-box for all. And then of course, you won't get away with this 56-bit key anymore, so this has a longer key. So more rounds, longer key. And now we said in a previous lecture that we, in any case, need to have something to authenticate. This was this message authentication code called MAC. And we only did some very simple designs, and I also don't want to cover more here, but there's some currently used ones called HMAC. There is it. So this is functioning the same way as we described, except for it's not just a hash function with the authentication key in the message, authentication key in the ciphertext, but it's a slightly more involved thing, which again uses an auth key in the message. There's one which is called poly1305. So these two are standalone. Max, that means they really function in the way that we describe them. You put in the message, or better put in the ciphertext, the authentication key, and you get an extra tag. So then you really have this modular design. You pick one of the block ciphers and a mode, or you pick a stream cipher. In any case, you pick an authenticator. What you see when you click on your browser, when you ask it like, hey, what are you currently using? I hope you don't see triple S. I assume you're going to see AES. What you typically see is AES, not with one of these, but you see AES GCM. So this is the name dropping session. I'm not going to cover any of the details, but what GCM is, this, well, it stands for Galois counter mode. So that is taking AES, which is one of the block ciphers. It takes a mode, which is close to the counter mode, and then this Galois comes from, they also use something with the fine field polynomial. So poly1305 is polynomial based, and GCM is also polynomial based. So this is a combination of block cipher mode and MAC in one. So the typical things you see is AES GCM. So if you have any recent browser and you go to any reasonable site, you will see AES GCM, or you will see a stream cipher called TanjaCrypt. So other recent choice. You will see TanjaCrypt, poly1305. Now, this is nothing we covered so far. This is a stream cipher. I mentioned grain, and when I said grain is, lots of people have looked at because we had a competition for it. TanjaCrypt, or at least its sibling Salsa20, went through the same competition and came out as one of the finalists, saying, okay, well, this is a good one, and then this is the MAC. On your current laptops, you probably always see AES GCM. If you have any recent websites, so if your website supports TLS 1.2, you'll see this one. If you're on your cell phone or if you're on a Chromebook, you'll see this one typically. So this really depends on what your hardware is and what site you're visiting. The high-end processors, like your big fat laptop, that one will have something where AES has hardware support, so that's something where it runs fast. And then the website says, oh yeah, we also have hardware support for this, let's run quickly. These guys are nicer for some hardware, well, for processors where you don't have hardware support for AES. That means that the Google end, for instance, has to do more work, but your cell phone doesn't drain the battery so quickly. So most pages now support both of them, and then depending what device you use to browse there, you'll either find this or that. So very important, don't just use a block cipher and a mode, you also need a MAC. Total context switch. I already introduced public key crypto last week because we needed it for the PGP part. And so far I only explained you that they have an encryption and a decryption. So already seen. The general setup for encryption and decryption. Now some of you who used the graphical tool for PGP, I got a question before like, hey, do you also want me to sign the message? If your tool asks you to sign it, it doesn't mean like putting a little ASCII block saying there, yes, I'm Tanja Lange, I'm a professor at Eindhoven, they actually mean a cryptographic operation. But we haven't done any of the signatures there. So that's what I want to cover now, is electronic signatures. And the idea of an electronic signature is somewhat close to what a MAC does, but it is in the public key world, whereas a MAC is in the symmetric key world. So a MAC is something where you both have the same authentication key. A signature is in the public key world, where you have two keys, a signing key, that is your private one, and a signature verification key, that is the public one. Now the reason that we call this thing signature is that it has the same function as your signature at the bottom of a document. Or if you look at like old documents, you have a proper seal on there. Like if there are multiple pages, you have a fabric, some thread going through, which is wrapping around once the whole thing. And then at the bottom there's this big wax seal saying, yep, this is combined, there's nothing missing, there's nothing added to it. And then the seal is something that's recognizable. Now when you see the seal, you can actually see, yes, this is valid, this was done by the city of Eindhoven, or a stamp or something. But you don't have the stamp, so you can't make it yourself. Similarly, a signature should be something that is easy to recognize as valid. When you see Tanja Lange written in my handwriting, you should be able to kind of 80% probable was me. In crypto, you would like to have 100%. But in normal handwriting, you're relatively sure it was me and not just some random person trying to imitate me. If somebody else writes Tanja Lange, it won't look like my signature. So you can verify it's from me, you still can't make it. So electronic signatures, like human signatures, or seals, or stamps, should be publicly verifiable and you want to have that they are authentic. And you want to have them linked to the document. So they also want to have that nobody can just change the document under it. I was saying, okay, if it's multiple pages, this thread goes through the whole thing, it bangs the whole thing. Or when I sign a contract, I have to initial each page. Sometimes I have to sign each page. So it's very clear that I have seen each and every page of the contract. And if somebody then goes with a ball pen and changes the letter there, then, well, it has been modified. So public verifiable is authentic and guarantee the integrity of the document. So for public keys, you have a public verification key. And you have a private signature key. So private signing key. Public key for verification. And then we have a secret key. The secret S for signing. And then the signer uses a secret key for signing. and then everybody can use the verification key to verify. So you sign a message or a ciphertext. For signature, doesn't matter whether it's public or secret. So let's just put a plaintext message there. In your application, it might be that you're signing the ciphertext. The signature doesn't care to what it's applied. It's applied to a bit string. So signer uses the signature key for signing M. Obtaining the signature S. And then the verifier, so anybody can verify that S is a valid signature typically you need the message for this. So a signature verification algorithm needs to see the message, it needs to see the signature, and it needs to see the public key. So we haven't seen any encryption or any signature system yet. Your PGP asks you at some point, hey, which one do you want to choose? Or it chooses for you and then says something about RSA. Some of you might have seen RSA before because it's like a typical case that math people were like, hey, math is useful. Look, we're dragging you through all this algebra and number theory, but it's also useful. We can do encryption with it. I don't know, who of you has seen RSA already? Many people have, not everybody. So math people have an advantage now, sorry for that. The first example we'll look at it's called RSA. Now, that is just 3 letters which doesn't tell you anything, and even if I tell you where these 3 letters come from, it won't tell you much. So RSA stands for the names of the inventors of this crypto system. So this is from 1977, due to Rivest, Chamier, and Edelman. 3, well, can I say computer scientists or mathematicians, so end of the 70s there was no clear distinction. I think today they would all, well, Edelman is more mathematician, the other ones are more computer scientists. 3 people working at the intersection of math and computer science. So RSA is due to Ron Rivest, Adi Chamier, and Len Edelman. And it's from 1978, that's 7 years. When you find a paper, it's from 78, depends on who saw it when, like publication date is after it was circulated. This came out a year, so in the lecture exactly 1 week ago I was saying 76, Diffie-Hellman said, hey, wouldn't it be cool to have public key crypto? Now they had one example in theirs which is not really public key encryption or signatures, and then a year later RSA was the first scheme which actually did full encryption and full signature schemes. So they had an idea of how one could instantiate this idea of Diffie and Hellman, and what they used was the example I was giving for a one-way function. It's easy to multiply the numbers, it's much harder to factor it. So this was the first public key system. Now, big warning sign, what we do now is a schoolbook version. And we'll see on Monday why this is a schoolbook version, why it's really bad to do it this way. But the main idea, the way that it's, well, if somebody gives you a properly formatted ciphertext or a properly formatted message to sign, this is totally fine. However, we need to figure out what properly formatted means, and it will mean that not every message is valid, not every signature, well, not every string M there is a valid message to be signed. So we have to do some pre-processing. That's not a problem. We're talking about numbers which are 2,000 or 4,000 bit long. All the messages you want to send are typically 100 or 200 bits long, so there's a lot of space for padding and formatting, whatever. So don't worry, it's all fine. We first need to understand what the math is doing, and then we can break it, and then we can try to kind of patch things. So the schoolbook version. So R, S, and A used that taking two primes so if you take P and Q and I want them to be not the same, then if you take two big numbers where we got them from, it's easy to multiply them. It is fast to compute N, which is P times Q. You all learn how to multiply, well, first you learned like how to multiply numbers up to 10. And it's easy because it's single digit. And then you learned how to multiply 2 digits, 3 digits, and at some point you figured out this whole way of taking any number of digits here times any number of digits there, and it depends on the school and the country you went to, how you write it, but you all know how to do long multiplications, like more than 1 digit. It takes you some time, but it's a finite number of steps. If you have 10 digits here and 10 digits there, you typically will do one operation with each pair of digits. So if it's 10 by 10, you will use 100 operations, and then you sum them up. It takes some time, but it's linear in the length. Sorry, it's quadratic in the length. It's not exponential in the length. So what I'm trying to highlight is it takes polynomial time, in this case quadratic, and you can do much faster with fast algorithms. So if you have n digits, m digits, it takes m plus n. So m times n. Sorry. Now this is fast to compute, while factoring n such an n, if you give me a power of 2 or if you give an even number, it's fairly easy to factor. So I want to have such an n, which is just the product of two primes. And I'll just write, it takes a long time. We will see a bunch of factorization algorithms, so then we can actually judge ourselves how long does it mean to take a long time. And there has been a lot of progress. So late 70s, it took longer to factor such a number than it takes now. But it's still something until we have a quantum computer that takes enough time so we can scale up our numbers. So long changed since the 70s. So now we use P and Q of at least each of them has 1024 bits. So when you look at the old documents from the kind of end of the 70s, their recommendations for how long these primes were, they're much smaller. That is an idea of how long does it take to factor a big number. But still now it is a hard problem to factor big numbers. So let's just take this as something which we will understand later and believe for now that factoring is a complicated problem. Now then, what can we build from this? So some math. should have seen Fermat's little theorem. Which says that if you have a to the phi of n, whatever that is common to 1 mod n. For a being co-prime to n. For if the GCD of a and n is 1, and this phi of n is Euler's phi function. Now if you tell me I've never seen phi of n, then I have to send you to the algebra course that's linked. So I expect you to have seen this thing. I'll quickly repeat what it does and how to compute it. But this is just going to be rushing through. The other way of searching with this thing, Greek letters are sometimes hard to search for. Writing out a Greek letter is also not helpful. The other name you find this is Euler's Totient function. Now, Totient function is a sufficiently weird word that it's at least Googleable, which doesn't mean it gives you better results than searching for Euler's phi function, but at least it will give you non-trivial results. So, for n equals p times q, we have that phi of n is equal to p minus 1 times q minus 1. And in general, if you have n being the product over some primes with positive exponents, where we don't want that they are the same, so pi is different from pj, and all the EIs are at least 1. So we only want to list primes that appear. So this is something you learned somewhere at school if you have a number split up into its factors. So if somebody gives you 21, you write 3 times 7. If somebody gives you 32, you write 2 to the 5. We don't want to write 2 times 2 times 2 times 2. So if it's 2 to the 5, we put the 5 up there and the 2 down there, and 32 doesn't contain any 3 or 5 or anything. So this is just a product over as many different prime factors as the number has, and we only put those where the exponent is non-zero. So in general, n is this, then phi of n is equal to the same product pi to the ei minus pi to the ei minus 1. First of all, is this consistent? Okay, I said p and q are different. So each of them has exponent 1. Then I would have the first one, exponent 1, minus itself to the exponent 0. Okay, that's the p minus 1 I see here, and then the q minus 1. For the 32, I would have e equals 5, p equals 2. So then I have 2 to the 5 minus 2 to the 4. So 32 minus 16 is 16. So this is how you compute it. If you have seen a slightly different form, you might also know this as n times the product over 1 minus 1 over pi. That's also, that gives the same number when you split it out. I don't know which one of these you have seen. Either works. This one needs fraction. This one only doesn't, so it's a bit nicer. So that's this magic function, and then Fermat's little theorem tells you that this function does something magic. So if you have a to the phi of n, we're getting 1. You can actually go one step further, where you don't have to have the GCD condition anymore. I'm not going to cover this in the next 10 minutes, but we will use it. So one can show that for n equals p times q, we even have if you take any a to the phi of n and we're computing mod n, getting the 1 here requires that I'll remove the 1, don't worry. Getting the 1 here requires that the GCD is 1. But if I multiply by a, so do phi of n plus 1 and a here, then it holds for everything. So let's do an easy example, a is 0. 0 to the anything will not be 0. 0 to the anything will not work with getting us a 1 here. And the GCD of 0 and n is n. But when I multiply by 0 on both sides, I get a true answer. Getting a, so 0 to something is 0. Nice. If I take p itself, then that's where it takes a little bit of work. So you're getting something which has p here, has p there. So it will totally flag this condition. And you trace it through and you're still getting p. So the same that holds for 2p, 3p, 4p, and so on. So we're going to use this generalization for what I'm going to show you now is RSA signatures. My public key, which is going to be the verification key, is exactly n and some e. And the only condition I have on e is that it's co-prime, can be random, so no condition other than that the GCD of e and this phi of n is 1. Okay. The typical choices you'll see are 3, 5, and 2 to the 16 plus 1. Of course, for exercises, we're going to go much more creative. We're going to use 7 or whatever comes to our mind. In reality, you'll typically, actually, not even 5 so much. You see 3 or 2 to the 16 plus 1. And then your private key will be the same e, same n, and then some d, where d times e is common to 1 mod phi of n. Also known as d is the inverse of e. D is common to e to the minus 1 mod phi of n. We'll do some diving back into what I hope you have learned already, namely how you compute those things. This was using the extended Euclidean algorithm to compute the inverses here. This is something you should have heard, but we'll cover bits of that. No, actually, we have seen the XGCD in the very first lecture in the Hill cipher. So when you broke the Hill cipher, there was this 2 by 2 matrix, you need to invert mod 26, and I said, okay, you need the extended Euclidean algorithm here. Same thing here, you pick your E equals 3, and then you compute D as the inverse of it. And then to sign M and more formatting needed. So this is why I said we're doing schoolbook method here. So right now we're just signing M, and on Monday we'll see how horrible that is. Now we're just interested in the functionality. We're not interested in somebody attacking us. So to sign M, compute the signature little s, which is just taking M to our secret key D mod N. Oh, that's nice. Just a one-liner, your computer can do that for you. It's just one exponentiation. And this should be lowercase. Now, to verify, now we need the public key, so this can't use D, this must use E. You want to check that S to the E is congruent to M mod N. Now, a check can fail or can be true. If it holds, the signature is valid. If it doesn't hold, the signature was invalid. Now, why is E signature that I make if I know the secret key here, if I know this is D, why is this giving me a valid signature? So a properly made signature passes. And this computation is just the same that when you learned RSA as an encryption in your algebra class or wherever you saw it. This is going to be exactly the same computation, just now we have used a signature key and you're now using a verification key, whereas back then you probably used an encryption and a decryption. Well, because. So we're starting over here with S to the E, and you want to do a bunch of computations where at the end we see M. Now S to the E, you have to remember where it came from, so S was the same as M to the D. Now we're computing this to power E. So what we have here is M to the E times D. Okay? Now I go back to here. D times E is 1 mod N. So we're going to use E times D is congruent to 1 mod N. That means E times D is equal to 1 plus some, yes?
Isn't that not 5 then?
Oh yeah, that's helpful. Else the next thing wouldn't help me much. Thank you. I hope I did it right here. Yep. Now that means if I take E times D, it's equal to 1 plus some multiple of phi of n. So plus some k times phi of n for some k. Alright, so I now will replace the E times D up there. So we have now equal to M to the E times D, or the congruences. E times D gets replaced by 1 plus k times phi of n. And in the end, I actually want something more than just the generalization I wrote there. I will want this with EK in front. And everything I said before for the 1 in front. So if it's co-prime, this gives 1, this still gives 1, so this will give A. For 0 it still holds, and for all the special cases that we would need to check, like P and its multiples, it also holds. So any multiple of phi of n plus 1 gives us exactly the result. So this gives us m mod n. So for valid signature we have that s to the e is common to m mod n. Now this doesn't tell you anything whether it's secure. It doesn't tell you anything what you could do with a signature to like take one signature and make a second one out of it. And those are the things that we of course need to look at in cryptanalysis, and that's what we're going to do on Monday. So that's it for today. Have a nice weekend.